you so much. Thank you, Shirshendu. So let me finish the part of yesterday, which was on observability of waves. Let me recall that we first reviewed the classical GCC sufficient condition for observability of waves for open subsets. Then I gave you some issues yesterday concerning generalization of this famous theorem to measurable subsets. As you could see, these are only partial results, and probably many of them can be much improved. This is my belief, but I do not know how to do. I mean, yesterday I essentially showed you how to consider interior and closure of omega, but I'm quite convinced there are many finer things to say. I believe, for instance, I didn't say it yesterday, I believe, for instance, that many statements can be derived if you consider bare subsets. There is a notion of bare set, bare of class 1, of class 2, of class 3, and so on. There are many subtleties about that, and maybe other notions I do not know, which is you assume some kind of regularity of the subsets. And I believe that many things can still be done in order to understand what happens. Yesterday, what I showed finally was quite rough in some sense. But anyway, and so I will finish this chapter by providing you with additional remarks and also another open problem on observability. I'm going to speak on spectral observability and also on quantum limits. And this will, by the way, make a transition to the last part we will start today. So first, what is spectral observability? Let me recall again, as I did many times, the definition here of the observability constant for waves and of the observability inequality that is here. You have here the sum of two half waves, and this energy is greater than the observability constant times the norm of the initial condition, right? This is the observability inequality. Okay, so this observability inequality is valid for any initial condition. I mean, what is an initial condition? It is a linear combination of all possible modes, right, in a spectral expansion. Now, what is spectral observability? It's a very particular case of this inequality in which you take a very particular solution, you take a modal solution, only one mode. So it means that in the inequality above, you choose, let's say, y minus equals 0 and y plus equal phi, where phi is an eigenfunction. So you restrict the observability inequality to only one mode, one Fourier mode, one eigenfunction, right? So here you assume that lambda, let me recall, it is square root of delta, right? So lambda phi equal to lambda phi. In what follows, we denote by E, by E the set of all normalized eigenfunctions. That is eigenfunctions of norm equal to 1, right? So what means spectral observability? It means that this observability inequality is satisfied for every such mode. So if you specify such a mode, of course you know the corresponding solution, right? If lambda phi is equal to lambda phi, then of course exponential I t lambda applied to phi, the corresponding half wave, is of course equal to exponential I t lambda times phi. So it's a particular solution of the wave equation. You plug it into the observability inequality, and then you obtain that inequality, which is, of course, weaker. If you just assume that the observability inequality is satisfied for every such mode, it is a weaker property, of course, strictly weaker, right? So this is the definition of spectral observability. There exists a positive constant such that for every normalized eigenfunction of square root of Laplacian, the integral over the whole manifold of a phi square is greater than c. I do not put the norm. You can figure out the norm of phi here, of course, but I took it equal to 1. Okay. Now we can, of course, we can define what is the best constant c. You have a new observability constant. You have a spectral observability constant. Let me give it a name. I denote it by G of A, right? This is my definition. So you can call G of A, let's say, why not, the spectral observability constant. This is the best possible constant appearing here. It may be 0. If it is 0, we don't have spectral observability. If it is positive, we have spectral observability. Okay? This is a definition. So of course, the best constant is what? It is this G of A, which is the infimum over all eigenfunctions of norm 1 of this integral. Right? So it's a quantity that is always greater than the observability constant. Because the observability constant, recalled above, is taken over all possible linear combinations of modes. It's a wider set. You take an infimum over a larger set. So it is, the observability constant is lower. Okay? Do not care so much about the normalization I chose, 1 over capital T and 1/2. We don't care. So you have this general inequality. It means, in particular, obviously, that if you have the observability property, I mean, if CT is positive, then G of A is positive, so observability implies spectral observability. But the converse is wrong, which is maybe not clear for the moment, right? The converse is wrong. We are going to see many counterexamples. It's not obvious that the converse is wrong. So it means here we have also a new quantity to explore. Yesterday I gave another quantity which was purely geometric, which was LT of A, you remember, which is the quantity measuring GCC. So basically we have two quantities, LT of A and G of A, to be compared with this observability constant. What do we have? We saw yesterday that I introduced, you remember, the high frequency observability constant, right? The observability constant CT of A divided by capital T was by definition less than the high frequency observability constant, alpha T of A. So it means that you have the inequality CT of A divided by T is less than alpha T, right? This was yesterday. But as we saw in the previous slide, CT of A divided by capital T is also now lower than G of A divided by 2, where G of A is the spectral observability constant. Also, we saw yesterday that when the function A is continuous, then the high frequency observability constant, alpha t of A, is equal to LT of A, right? LT of A is the quantity measuring GCC, the infimum over all rays of the trace in time led by geodesics. So it is tempting to wonder whether this inequality that you have here would be an equality or not. Personally, I think it is an equality. I'm unable to prove. It's a conjecture, it's an open problem. I think this is an equality, which would be a good result, right? Because it would say that the observability constant is made of a part that is purely spectral and of a part that is purely geometric, which corresponds perfectly to the intuition. Why? Because this part, the LT of A, the geometric part, as we saw yesterday, stands for high frequencies. This part, the spectral part, well, stands for both, but implies in particular the low frequencies. So this is why I believe that there is an equality. What we are able to prove is only, well, okay, it's already a result, is only that we have the equality at the limit in time. The limit in large time of the observability constant divided by capital T. You see, this is why I divided by capital T. It was necessary. The limit is equal to the minimum of these two quantities, spectral and geometric. And maybe you know about a famous result by Gilles Lebeau in '96 about the best decay rates for damped wave equations. No, you don't know? Look at this paper. It's a beautiful one, as many of papers by Lebeau, by the way. But this one is very beautiful. Lebeau characterizes in his paper the best decay rate for damped wave equations as a minimum of two quantities. One of them is the spectral abscissa of the operator, as you would expect. And the other quantity is that guy. He does not write it exactly like that, but it's exactly that. And so, there is a strong similarity. And probably it is more than a similarity because, as I told you yesterday, there is a strong relationship between observability and exponential stabilizability by the arrow theorem. And so maybe this result and the result by Lebeau are the same, maybe, I don't know. I'm unable to see that, but there is an evident relation. Anyway, I let you with this open problem, which is quite interesting, I think. Okay, and also as a transition to the part that will follow, let me recall or maybe introduce the concept of quantum limit, which is a particular case of the concept of microlocal defect measure or semi-classical measure that you saw with Belassen last week. It's a particular case. Let me introduce it naively. You take, you take phi j, or phi, okay, phi j, which is an eigenfunction of the Laplacian, right? So by definition, delta phi j is equal to minus lambda j square phi j, an eigenfunction. I take it to be normalized. I mean the L2 norm of phi j is equal to 1. Then I take the square of the absolute value of it. I take, let's say, the normalized Lebesgue measure on capital omega. Normalized. I should divide maybe by the volume of capital omega. Okay? I mean, you take the Lebesgue measure so that the Lebesgue measure of the whole capital omega is equal to 1. Okay? Normalized Lebesgue measure. Now, this guy, well, this guy is a probability measure. This guy is a probability measure. Because mu j of the whole capital omega is equal to 1. But now, the set of probability measures is compact, right? Weakly compact. It is a Prokhorov theorem or something like that. Or maybe Banach-Rallo glue for analysts. It's the same. It means that up to some subsequence, of course, you take a subsequence, and there are some subsequences that converge weakly to some probability measure. Weakly star. So such a limit is called a quantum limit. It's also called a defect measure. It's also called a semi-classical measure when you look at them from the microlocal point of view. I mean, if you look at them from the microlocal point of view, oh no, I will not introduce that. We don't need anyway. So this is the definition of a quantum limit. Well, so let us come back to the spectral observability constant, G of A, which is by definition, let me recall, the infimum over all normalized eigenfunctions of the integral of A against phi square. Now you take high frequencies, I mean, in G of A in particular, you have G of A which is less than integral over omega of A phi j square dx, right? For every j, by definition. But this guy is exactly, with my notation, it's exactly mu j of A, right? That is integral of A d mu j. And so it means that if you pass to the limit, you let j tends to the infinity and you obtain less than mu of A by weak convergence, right? So what I say here is that G of A, this quantity, is less than the infimum over all quantum limits of mu of A. Is a fact. By the way, in some of my papers, I also give a name to that quantity, because this quantity has a meaning. But here, what is of interest is that because of that inequality, you see that a necessary condition for having spectral observability is that you must have mu of A positive for every quantum limit. This is a necessary condition, which should motivate us to study quantum limits, to try to compute them, because they will give a necessary condition. So we have to understand them. I will come back on this issue, which is very related to an emerging theory in mathematics since 15 years maybe, which is called quantum chaos. And one of the main issues, one of the main questions in quantum chaos is the question of knowing how to compute quantum limits. I will comment on that rather tomorrow in due time, but you can already think about that and review, let's say, the configurations for which you would be able to compute them. You will see that there are only very few. The question is essentially open. It's very much interesting. Okay, so that's all for the moment. It's a kind of teaser to the next part. So the next and last part of my lecture is now so we investigated very much observability of wave equations, in particular on measurable subsets. This is also because we want to act on the subset small omega. And in some sense, the natural question that emerges would be to be able to choose the best possible subset omega in some sense. What is best? We have to define this notion. We would like to be able, in some sense, to promote observability, to maximize this observability property. So let us try to, in this last part, we are going to try to give a sense, because there are many possibilities to give a sense to the problem of optimal observability. Here I will propose one. Then we will try to solve the problem. We will see that the problem has a closed relationship with quantum chaos, as I said. And we will solve the problem not only for waves, because for waves, essentially, I give you the answer, and there is no answer, mainly. The problem is not solvable. There is no good answer. But in contrast, we will see that, and at the very, very contrary, there is a good answer for parabolic equations, like heat equations. This is why we will solve the problem of optimal observability, both for heat and wave equations. You will see there will be an enormous contrast in between. Okay, so let us go to this problem, and let us first ask the informal question. For the moment, it has no mathematical meaning. What is the best possible observation subset? What is the best possible shape and placement of sensors? I mean, you want to observe some system in some domain, capital omega, maybe in the interior of omega, maybe at the boundary, like it is for the human body, for instance. In that case, sensors normally are at the boundary, right? And you would like to be able to place optimally the sensors, and not only to place optimally, also to shape them optimally. Okay, so it will be a problem of shape optimization. Why do we want to do so? Because obviously, in inverse problems that are behind this kind of question, we want to maximize some efficiency, obviously. And we want also to be as cheap as possible. We want to reduce the cost of instruments. Right? So we would like to be able both to maximize observation with a minimum of material in some sense. So this is why there are plenty of models for that. I will propose one. So the systems that we are going to investigate in this part are primarily the wave equation, as we did before, but also, as I said, more general parabolic equations, such as heat or Stokes equations, something like that. In what I will say, you can have domains with a boundary, and you can take either boundary conditions at the boundary, whatever. For instance, this was to my son a long time ago, more than 20 years ago. Memories. For instance, when we deal with the heat equation, we will want to know this. We will want to know what is the optimal shape and placement of a thermometer. We will solve the question. So we will arrive at a thermometer which, as you can guess, does not have the usual shape. It's a mathematical thermometer. Okay. So let us discuss the model that we will use. First, as we reviewed very much during the lecture, let us consider again the wave equation. And when the wave equation is observable, you have an observability constant, right? You have an observability inequality with an observability constant on which we talked very much. Right? And we know that the observability constant is positive under GCC. We saw all of that, right? So let us look at this observability inequality. What is observability? Let me recall in words. Observability means you have a domain, a room, a cavity, something like that, capital omega, inside of which, somewhere in the room, you have put some sensors, maybe a thermometer, maybe something to capture waves, something like that. Sensors. Sensors are modeled mathematically by the subset small omega. What means observing the wave equations? It means that on the subset small omega, you assume that you are able to measure exactly the solution of the waves. You take measures on small omega. Mathematically, it means that you have the knowledge of the solution of the wave equation that is arriving in a small omega. You know it only restricted to small omega. And this measurement, you perform it over a certain horizon of time, capital T. So it means that you know this quantity in particular. You know this restricted energy of the waves. You know it. You measure it. And just with this measurement, you would like to be able to reconstruct the whole wave, the whole solution. So in order to reconstruct the whole solution, you just need to reconstruct the initial condition. Because once you know the initial condition completely, you just have to integrate the wave equation. Right? This is the problem of observability I recalled yesterday or the day before. So in order to have observability, I recall what I said before, you need to have an injectivity property, which is there. I mean, here, if the measurement is identically zero, then you would expect that the whole wave is zero. You would expect that the initial condition is zero, which is the injectivity property, approximate controllability by duality. But if you would like to reconstruct, you need more. You need to quantify, and this is why the observability, I mean with a positive constant here, is so much important. You also feel with what I say that now if you try to implement an algorithm which solves the inverse problem, I mean, from the knowledge, from the measurement on a small omega, you would like to have an algorithm designing a good estimate of the initial conditions, whatever the algorithm will be, right? You certainly know plenty of algorithms for solving inverse problems. This is not my concern here, right? But what I can say certainly is that whatever the algorithm will be, the quality of the algorithm, the convergence of the algorithm, will certainly be related strongly to the value of the observability constant, right? And you have an interest in having an observability constant which is the largest possible. Of course. Why? Because imagine that you have observability, but with a very, very small constant. Imagine. It would say the system is little observable. What does it mean? If this constant is very small, then put it on the right-hand side. 1 over c. So 1 over c is now very large. So it means that if you make a small error, a small mistake in the measurement here, it will be multiplied by a big number. And so you will have a big error here, right? So numerically, from the point of view of numerical analysis, you see that inside this constant, there is the notion of conditioning. This constant, the value of this constant, exactly stands for some good conditioning of the inverse problem. So this is why certainly we should try to maximize this observability constant. You agree? No. But this observability constant, okay, it depends on capital T and on omega, right? So capital T is the time spent to make measurements. Okay, I don't know. 1 minute, 1 day, 1 month, I don't know. This is determined by the conditions. But at least you can act on the choice of omega. This is your choice. So you should try to choose small omega so that the value of Ct of omega will be maximal possible. It will be good, this for sure. And actually, well, I'm mentioning here a paper that I have written with Jérôme Le Rousseau, Gilles Lebeau, and Pepino Terpolilli, because it's an extension of GCC on time-varying domains. I did not speak about that, but this is when you allow sensors also to move. And so certainly you know the names of Le Rousseau and Lebeau, but maybe not this guy, because this guy is an engineer in Total Energy. He's looking for oil in the soil. And of course, they have some sensors, and sensors are moving. And they have a strong interest, of course, of trying to design what are the best possible shape and placement of sensors. So the question that we solve in this paper, which is purely theoretical actually, but solves actually, but we didn't publish that, a very practical question. The very practical question was not published, of course, as you can imagine, because it is confidential. But it motivated, for a large part, the problem of maximizing the observability constant. Okay. Well, a first obvious remark. So for the moment, the informal question is, okay, are we able to determine what is the best possible subdomain on which you have a maximal observability? Of course, if I do not make any restriction on small omega, you have an immediate answer. take small omega equal to capital omega, and you are done. I mean, obviously, you put sensors everywhere in the room. And yeah, of course, it's the best possible. In that case, clearly, the observability constant will be maximal possible. Yeah, but it's not reasonable, right? It's not reasonable. We only have a limited quantity of sensors. Maybe we are allowed to put a device here, like that, and maybe somewhere else, but not over the whole room. I mean, basically, the Lebesgue measure of small omega should be limited. So this is where this first restriction comes from. In all what follows, we will fix a real number, capital L, which is between 0 and 1, and we will restrict to those subdomains, small omega, that have a fixed Lebesgue measure. Or maybe you can put, instead of equal here, you can put lower of equal, or equal. It will be the same. Any optimal set will saturate the constraint anyway, you feel it. So let us put equal, okay? For instance, if L is equal to 0.1, it means that you can spread some sensors in the room over 10% of the room. So it is a natural restriction. Now so this was the observability for waves. Let me recall quickly the observability for the heat equation. So if instead of looking at the wave, you look at the heat equation, Dirichlet, for instance, you can define the observability constant exactly in the same way as before, except that here you are dealing with exact null controllability. So by duality, you deal with finite time observability. This is why here you don't have y of 0, but y of capital T. Probably this was recalled by whom last week? Marius? No, not Marius. Who did that? Marius did that? Okay, good. Anyway, so you have exactly the same definition, right, with obvious adaptations. And what is known about the heat equation? Well, it is known, so in the 70s first in 1D, and then in the 90s in multi-D by Lebeau-Robiano and Emmanuel Trélat, and also Fursikov, by the way, that as soon as your subset omega is of positive measure, you always have observability. It's a good result. You don't have any GCC, nothing. It always works, at least as soon as the set, of course, is non-trivial. You always have observability, and moreover, observability holds in any time capital T. It's a strong result. Okay, so, but in that case too, given some time capital T, we will want maybe to maximize this observability constant. For the same reason. I would like to stress that we do not want only to optimize the placement of the sensors, because maybe, okay, imagine this is a sensor. This has a fixed shape, right? And I would like to place it optimally in the room, right? So in that case, my only unknown is a point, okay? And then it is a finite dimensional optimization problem. It's not only that. I would like also to act on the shape. So I have a subset, and I can choose also the shape. And by the way, maybe the set is not connected. Maybe the set has several connected components. Maybe it's fractal. I don't know. So we do not want only to act on the placement, but also on the shape of omega. Of course, you will tell me, maybe in practice, we never act on the shape. And you are right. This is a question for mathematicians, I agree. In practice, a sensor is, let's say, a given device like that with a precise shape that is chosen in advance, right? I agree. So this is rather a question for mathematicians. Anyway, it's an interesting question. We would like to shape optimally this sensor. And we do not want to make any other restriction. I mean, we do want to search the best possible set over all possible measurable subsets. We are mathematicians, so maybe we want to know if the best subset will be a fractal. I mean, why not? That's life. Huh? That's life. We want to know that. So we do not want that the subset be BV or whatever. Do not want to make any restriction. Because you could do, and this is what people usually do in shape optimization, you know. Have you ever met some shape optimization problems? Most of the time, in order to to prove the existence of a minimal set, they add some requirements, like the BV norm of the subset is bounded. Or maybe the number of connected components of the set is bounded, or maybe the perimeter of the set is bounded, or something like that. Because, why? Because mathematically it's very convenient. As soon as you add such a requirement, you have compactness properties. And that's good, of course. That's very good. But we would like to avoid that kind of restriction, because even without this kind of restriction, we would like to know if there would exist a very best subset, small omega, which is maybe not BV, which may have an infinite number of connected components, or I don't know. We would like to have the true answer. Okay. So let us come back, let's say, to the wave to give a support. So it seems that it's quite natural to investigate this problem, right? We want to maximize the observability constant over all possible measurable subsets, small omega of capital omega, that have a fixed Lebesgue measure. It seems reasonable. But, well, very quickly we are stuck. We are stuck, completely stuck, because this problem is extremely difficult. Why? Because, okay, you are maximizing this functional constant, which is itself an infimum. So it's a problem of sup infimum already. Right, so it's not nice. It's not easy. And to see that it is not easy, let me see, yeah, after. To see that it is not easy, let us perform a spectral expansion again of the wave equation, or maybe of the heat equation, right? In that case, and we saw that yesterday or the day before, the observed energy is a double sum of terms. It's a double sum because you expand, right? You expand this infinite sum, you obtain a double sum here. So in particular, you have many crossed terms. And the expression for the coefficients alpha ij is very bad. It's here. So here is the problem that we would have to solve. Look, maximizing the observability constant means maximizing over omega the minimum over all L2 sequences aj, bj of a double sum, which is not so nice, right? Not so nice. And I insist, we want to do a mathematical theory, because the question of numerics is something else. Actually, to underline the difficulty is due actually to the crust terms. This is because you can also see this expression as the Gramian, which is applied to initial conditions. And here, the main problem is that the Gramian of the wave equation, or maybe the heat equation, is a full matrix. Actually, the coefficients that you see there are exactly the coefficients of the Gramian, which is a full matrix. So, again, how to compute the lowest eigenvalue of such a full matrix, a full infinite dimensional matrix. I would like to underline also that you have exactly the same difficulty in the problem of determining what are the optimal constants in Ingham's inequalities. Do you know that problem? Or do you want me to spend several minutes on that? No? You decide, you are the boss. It's not known, yes. Let me show you. This is the Ingham theorem, right? The Ingham theorem, which is easier than the previous one, right? Because there is no x, there is only t dependence here. And already here, believe me, it's difficult. It's difficult. So what says the Ingham theorem? The Ingham theorem says you take a kind of Fourier series here. Not exactly Fourier, it's anharmonic, right? It means that you take some of complex exponentials in which the mu n are, let's say, some real numbers, and you would like this corresponding quantity, which makes you think of Parseval, right, when you have a true Fourier series. You would like this quantity, you would like a Parseval theorem, actually. You would like this quantity to be equivalent to the sum of an square. So you perfectly know that this is true when you have a mu n equal n. This is Fourier. This is Parseval. And what the celebrated Ingham inequality says is that this is also true when the mu n have a gap, a uniform gap. When there is a gamma which is uniform and which is bounding below mu n plus 1 minus mu n. Oh, I forgot to say that the mu n are an increasing sequence, sorry. Okay. So in that case, you have this equivalence. You have a kind of Parseval inequality. And Ingham proved in his paper more than 1 century ago, Ingham proved an estimate for the constant. It's inside his paper. But still, until now, the best constants are not known. It is strange, right? Because the problem does not look so much difficult. But it is. It is. It's an open problem. Interesting. Interesting. Actually, I know only one case where you know the optimal constants, but it's quite obvious. It's when mu n equal n. You just have to check. It's easy. It's very easy. In that case, yes, we know the best constants. It comes from Parseval. It's easy. Otherwise, you don't know. You don't know. It's likely that in the literature, maybe some people have established even better constants. I do not know so much. Anyway, the proof, by the way, the proof is interesting. The proof is there. The proof of Ingham is there. I don't advise that you look the historical proof by Ingham because you do not understand the idea. This guy was very tricky. But actually, the true trick is just in the Fourier transform. That's easy. You take this quantity, you take this integral, but inside this integral, you insert some Fourier transform of some function that you will choose. I mean, why not? F hat of t. Then you expand the square. You obtain this double sum, right? But there, integral of f star times this complex exponential, you apply now the inverse Fourier transform. And this guy here may be divided by 2 pi or something. We don't care. This guy, by inverse Fourier, is exactly f of mu j minus mu k, right? Now, this computation was obviously valid for any function f. Okay? So you choose now f. And you choose an f, you choose a bump function like that, a localized function, so that the support of f is in between gamma over 2 and minus gamma over 2. Just that. So that this term here is 0 as soon as j is different from k, because of the gap assumption, right? It gives you the proof. So you just have to, in his paper, I don't know how he did, but Ingham does not use at all inverse Fourier transform. He does it indirectly, and he chooses the good function. I mean, there are quite natural choices, quite optimal in some sense, and this is the choice by Ingham. But this is I would say, the modern version of the proof. So this is just to say that coming back to the observability constant, we could follow the same, but well, I don't know then how to deal. I don't know. So I don't know. So let me take another bias. And the other bias is that finally, and this remark is due to my engineer colleague, Terpolili, he told me, okay, but personally, I do not care with the observability constant. I do not care. Why? Because the observability constant is purely deterministic. If you look at, again, the observability inequality, which is here, actually, this observability constant, which is an infimum, finally stands for the worst possible case in this inequality, right? It's an infimum. It's an operator norm. So it stands for the worst possible case. That's okay, but once we have shaped and placed some sensors, we are actually making hundreds and maybe thousands of measurements, not only one. So maybe what the engineer told me is, okay, maybe sometimes some measurement will not be useful because you fall in the worst possible case, maybe, but we don't care because you are doing 1,000 measurements. So maybe if 1 or 2 are not good, we don't care. What would be great is that in average, things are good. So actually, it's a good idea here. Here you see this is a for all solution, right? Actually, what would be great is to replace the for all by a for almost all. And this makes an enormous difference. Maybe sometimes you will have a solution that is invisible. Okay. Is it so serious? Maybe not, because maybe the set of invisible solutions will be very small with respect to all solutions. So this was this idea that led us to define an alternative notion of observability constant that we called randomized observability constant, which is there. We will replace the previous constant by a randomized observability constant, and we will replace the observability inequality by this new inequality with here, you add an expectation, an average over all possible probabilistic initial data. You want that things are good in average. Now, that's one thing. Now we have to turn this intuitive idea into some proper and rigorous mathematics. And thank you very much to Nicolas Burck, because he gave me the crucial idea. He told me, okay, there is a simple trick, a very simple trick I would like to share with you in order to turn a full matrix, a full Gramian matrix, into a diagonal matrix. And this simple trick is not even an idea by him, actually. I will explain. But this simple trick consists of looking at, again, the solution of the wave equation that is there, but in front of each coefficient, aj and bj, which stand for the initial data, right? You will add a probabilistic law. Typically, you will multiply by plus or minus 1, just that. You take a Bernoulli law, just multiply by plus or minus 1, with probability 1/2 each time, right? You take this, okay? So instead of aj, you have plus or minus aj, with probability 1/2. Okay, but you can take whatever probabilistic law that you want, actually, but take plus or minus 1. And then compute again the quantity. Then you diagonalize the Gramian matrix. Look, it's very easy. Look. You take the same quantity again, but now you have inserted this probabilistic law, plus or minus 1, and then you will take the expectation of the result. This is the new quantity of interest. Okay, so let us do the computation. It's not difficult. You expand the square, you have a double sum, but now in the double sum you have a new term, which is the expectation of the crossed coefficients, beta j, beta k. Yes, but we took them IID. We took them independent one from each other. So as soon as j is different from k, this guy is equal to 0. You kill all crossed terms. And when j is equal to k, well, you have the expectation of 1, which is 1. So this is why this double sum, in this double sum, you kill all terms outside of the diagonal. You just keep diagonal terms, and it gives you this quantity. Sum of aj square, integral of phi j square. And then you take the infimum of this quantity over all sequences aj such that the sum of the square is equal to 1. What do you obtain? You obtain exactly the infimum over j of integral over omega of phi j square. Right? Which is, look, which is exactly the g of omega I introduced previously, right? So actually what I say here, I do not remember if I wrote that, or maybe, no, I did not write it, but for the waves, the randomized observability constant is exactly equal to g of omega, the spectral quantity. It gives a new view on what I said previously. Right? The spectral quantity g of omega, which appeared in the minimum of the two quantities. Right? Actually, this guy is the randomized observability constant. It has a true interpretation, a probabilistic interpretation. Do you just give me 5 minutes? Thanks. I would like to tell you about this, this story that Nicolas Burke told me. Because what Nicolas Burke told me, so it was, I don't know, maybe 10 years ago, something like that. He told me this trick. This trick is due to Nicolas Burke, but actually not due to Nicolas Burke. It's due to Paley and Zygmunt 1 century ago. In the year 1930, Paley and Zygmunt investigated the following question. Look, let us define in 1D a Fourier series. Right? A Fourier series on 0p. Okay, it's always like that, a Fourier series. Now, what you know about the Fourier series is that, well, you have Parseval. So what does it mean? It means that for every aj in L2, obviously f is in L2, right? This is what we learn in first year at the university. Okay, so the question asked by Paley and Zygmunt was, okay, but can we do better? Can we replace L2 with LP for any P? Well, the answer is clear here. No, obviously no. No. But they said, okay, the answer is no. That's right. But now, is it true for almost every sequence aj? And then the answer is yes. And their trick was to say, okay, let us multiply aj by plus or minus 1 with the Bernoulli law. Or more generally, let us now set f of t equal to the sum of epsilon j, aj, epsilon ijt, with epsilon j, which is probabilistic. There is an event inside each of them. Now the claim is that almost surely f is in LP for every p greater than 1. Incredible, no? No, assumption. Ah, on epsilon j? Oh, you fix an aj in L2. Yes. Yes. Let me do 2 minutes, it's okay? Let me make the proof. Actually, let me prove, because it's the same, let me prove that f is almost surely in L4. Almost surely. It suffices, because then you can make L8, L16, and so on, and conclude by interpolation. Let us prove that fact. Actually, let me compute integral of f to the power 4. And let me then take the expectation. What we want to prove is that this quantity is finite. Because if this quantity is finite, then this implies the statement, right? So let us prove that fact. Let us compute this expectation. It's not difficult. It's not difficult because this expectation is equal to a sum over 4 indices, right? Sum over J1, J2, J3, J4 of, so you expand. You have epsilon J1, epsilon J2, epsilon J3, epsilon J4 times AJ1, AJ2, aj3, aj4 times integral of exponential I j1 plus j2 minus j3 minus j4 t. And there is some bar here, and there is the expectation here. Okay? Now, you see that these expectation terms are always equal to 0, except when the integers j1, j2, j3, and j4 are pairwise equal. Okay, the only cases where this expectation is not 0 is whenever g1 equal j2 and j3 equal j4, or j1 equal j3 and j2 equal j4, or j1 equal j4 and j2 equal j3, right? You have 3 cases. Let us take one of them. Let us take, say, j1 equal j3, j2 equal j4. In that case, you are back with a sum over 2 indices, let's say p and q. This is p, this is q, okay? Of ap square aq square, and that's all. And what is it? It's exactly sum over j of aj square to the square. So it's the norm of the non-probabilistic function. So sum of aj exponential ijt L2 to the 4. So it's finite. And we are done. It's surprisingly easy. And for me, it is still a surprise that such a beautiful result is so powerful. So I repeat, the initial question was, okay, I take a Fourier series, usual in L2. When can I say that it is in LP? Well, almost always. This is the answer. 1 century ago. Almost always, the Fourier series is in any LP. And this is the argument. And so, you see, what Nicolas Burck took in this incredible argument is this idea that you can kill crossed terms. And generously, he gave me the idea. And I was very happy with this idea, as you can imagine. Because I wrote maybe 4 or 5 papers just about that. I will tell you tomorrow then how to solve what follows, but I was happy to give you this beautiful trick.
Thank you, Emmanuel, for the very nice talk. So now I ask the audience if they have a question, they can ask Emmanuel, or also if in online, if there is a question, they can ask.
Yeah, right. So if instead of Bernoulli, you take any random variables, so the basic assumptions that you need, that you see there on my computation are, you take them IID always, you take them of 0 average, and you take them of, let's say, fixed variance, uniform variance. I mean, the expectation of epsilon j to the square should be equal to some fixed number, not depending on j. And then the computation is perfectly okay. That's all. Very few. Very few. But actually, so this is very, very well explained, maybe not in this paper, because this paper is complicated and deals with completely other issues concerning blowing up. It's very well explained in 2 papers by Nicolas Burck, his ICM proceeding paper. So it was ICM 2014, I think. Yes, 2014. And in proceeding Edinburgh, Shirshendu, help me. 2016, maybe. I can send you the papers if you are interested. But these are two elementary papers in which Nicolas Burke reviews the very basics of this idea by Palais-Zygmunt. And also he gives, some large deviation theorems. Very, very much interesting. It was not useful to me in my framework, but it can be useful sometimes. You may want to use large deviations estimates. And this is extremely elementary. So very beautiful.
Question that, is it suppose you have a one parameter system given by this gamma. The system of wave equations parameterized by this gamma. The average controllability.
What is gamma? Sorry. What?
You have observations in the y of gamma, y of the parameter.
Oh. No, it was
here.
Here.
Yeah, no, not the next slide.
Yeah.
No, not this one. In the observability here. The right hand side, you take the expectation of that y new, right?
Oh, this is the event.
So this one, in the case of a system of wave equation parameterized by this, is it giving you exactly the average controllability of that one?
I did not understand your.
Is it giving the average controllability of the system?
Is it average observability?
So that's why I'm asking. Is it?
When do we have average observability?
Yes. Is it giving you that parameter system indeed, this one?
Oh. Yeah, okay. Okay, sorry, I did not understand Shirshendu. So since the randomized observability constant coincides with the spectral observability, we can just assert that we do have randomized observability property if we have the spectral observability. That's all. The two notions coincide. This is my claim. Randomized observability is equal to spectral observability. It's the same notion. And so this is why you have to understand the concept of quantum limits. Because we have to understand when we can say that the quantity G of A or G of omega is positive.
And just again, I'm saying, so suppose you have a wave equation, the WTT minus, in front of Laplacian, you have a viscosity parameter, which I don't know. For that one, now then this parameter varies over some set.
Yeah.
And then you have a family of wave equations.
Yeah.
And now you use a single control to get the observation, but in the sense of average.
Yeah, okay.
Is it the same thing this observability is giving you essentially for the whole family of the system, this inequality?
Okay, so I'm sorry because I completely misunderstood your question. So you want to act on the viscosity parameter and make it probabilistic, probably.
Yes, so this is...
It's not the same. It's not the same procedure because here what we do is randomize the initial data. We do not randomize the operator.
Okay.
We do not.
Okay.
It's something different. If you randomize the Laplacian, then you will have probabilistic law inside the
Lambda J, yes.
And so, good idea, but I do not know. Just have to make the computation.
Okay, because
I never thought about that, but you can.
No, because there is one paper in 2016 by Zua in average control. So this is...
No, it's completely something else. What does Enrique in this paper is completely something else. No. It's much more elementary. Much more. It's also very much interesting, huh? But it's not it's not the same. No. And by the way, the objective of Enrique in this paper was to show that with his concept of average observability or controllability, you come out by duality with new observability inequalities in which you don't have the square inside the integral. It is a L1 norm, which is very much interesting. But it is, it is something else. Here, yeah, you have a good idea, Shirshendu. It's for lunch. I do not know what we could get from putting the beta inside the exponential. I don't know. We'll do that during the lunch.
Okay, yes, I have another question. So the first one is technical. Say, can you go back to the proof of Ingham? There is something that I have missed, probably. Yes, yes, here. So I have understood how you deal with the right-hand side term, taking taking f as the bump function, but how to deal to the left-hand side, because the Fourier transform of f.
Sure,
yes.
I did not tell that. You are right. Choose a bump.
Yes.
Well, yeah. Choose a bump that is like a Dirac.
Okay.
What is the Fourier transform of the Dirac? It's 1.
Yes, okay.
This is the idea.
Yes, okay.
If you take f close to the Dirac, you get 1 here.
Yes, okay.
If you take an approximation, you do not get 1, but you get something which is expected to be close to 1.
Okay.
And it is sufficient.
Okay. Yes. And I have another question, just to think about generalization, also from a mathematical point of view, because I believe this would be difficult for application, but there is a recent paper by Burke and Moyano who proves that the heat equation is observable, let's say in a weak sense, with sets that are not of measure equal to 0, but with Hausdorff measure not 0. And can you imagine that you can generalize what you have done with maximizing the observability constant or something like that in this spirit?
This is, certainly this is an open question.
Yes.
This question echoes the open problem I told before, which was already how to generalize GCC. So it was for waves, not for how to generalize the properties of GCC and so on to subsets that have good regularity properties. So there, what they do, their idea is to look at subsets that have a positive Hausdorff measure. Right? So like an infinite number of hyperplanes, for instance, something like that. Because they care, they do care sufficient information, evidently. No, to be frank, I do not know.
Yes, okay.
I do not know.
Okay, thank you. Thank you very much.
Maximizing over that, I do not know.
Yes, okay.
It's completely open.
Yeah, I imagine. Okay. Thank you.
So I have a same question in the same spirit. Suppose you have a heat equation in unbounded domain, and omega is the so-called thick set.
Omega is, sorry?
So-called thick set, no? This,
a thick set.
Yeah.
A thick set, yes.
For that kind of, this kind of problem, like optimizing.
So thick sets are used, for unbounded domains.
Unbounded domains.
Unbounded domains.
Yes.
All what I did was, you are right. All what I did is for bounded domains. I never investigated those problems for unbounded domains. But of course, you are right. We can bet that if we work in the whole RN, thick sets will be very, very useful, for sure. But I did not investigate in this
And
direction.
just one more question. So suppose if you fix the number of connected components, let's say 1 or 2, the problem is, as you said, like is easier.
Other things that L2
No, just let's say in bounded domain, and you said the omega is just one component, let's say ball.
I'm sorry, I was not able to understand.
So let's say you have a OAB equation, and OAB or heat equation, and then omega is a ball.
Omega
is a ball of radius 1, or let's say. And then you do this shape optimization or this finding the observability constant.
Yep.
Is it possible? Not going to the randomized initial data?
I don't know. I don't know at all. No, it's open, I think. It's open. Many things are open,
Just clarification.
Yes.
When you show that the observability, and can you go to the slide where you show the inequality, that one side, the observability is essentially implying the spectral one, because you have the summation in terms of the Fi. So can you go that slide?
So it was a bit before that. This one?
Just before that.
Just before here.
This one is written, observability is any time the spectral observability. This is okay. Because you have if you have the observability, then for any eigenfunctions you will get it. But what is the thing that suppose you have for any eigenfunctions this one, with extra which quantity it will give you the back?
You will see that tomorrow. You are too much impatient.
No, because there are some we use this opposite way because there are some systems which are not spectrally controllable.
Yes.
That's why we know that one, like damped wave equation, it is not observable.
Yeah, yeah.
So the point is, if you have this spectral observation for certain sets, a set where this epsilon, that's denoting that set, can I conclude anything about the observability related to that set? The span of those functions on that set?
You will see tomorrow, but the short answer is no.
No.
No. No. Let me just give you an example, but I will comment it tomorrow. You take the square, capital omega is the square, and this is small omega. Obviously, GCC is not satisfied, so the observability constant is equal to 0. However, you have spectral observability there.
I'm not saying about the observability on the whole set, whole space, the base space. Is it possible that is getting the observability on a subspace?
For the best space, you will see that tomorrow.
Thank you.
You want me to spoil what I will say tomorrow, yeah. I won't.
Again for the nice lecture.